Okay, let's continue the discussion. In the last video, we proved this nested interval property. When you have this interval, a sequence interval, you shrink this interval, then the intersection of all these intervals has at least one number. If the interval has length converged to 0, then it contains only exactly one number. Okay, so you just use that increasing sequence. Bounded increasing sequence has a limit, bounded decreasing sequence also has a limit. Okay, and in this theorem, there are several conditions. So a non-empty, of course, it has to be non-empty. So basically, there are two important properties. One is called closed, the other one is called bounded. Nested is always nested. You have to be one inside the other. So we are going to have two remarks, basically two examples, which shows you cannot remove either of them. Okay, so the nested interval property does not hold if the closedness is omitted. Okay, so we just once it is not hold, when you want to claim some statement does not hold, you just find an example. So we check an example that I be what? Be 0, 1 over n. It's not closed, but it has all other properties. It's nested, it is non-empty, it is bounded. It's nested, non-empty, bounded, but not closed. We can see that the intersection of I is an empty set. It does not contains anything. All right, so it does not satisfy the condition that it contains the intersection contains at least one element. You have to have closeness. Okay. Second, the nested interval property may not hold if boundedness is omitted. If you do not have a bounded set, then you may not have a non-empty intersection. So the example is the following. We let I be, so this time we still keep the closeness. So this is a nested, non-empty, and closed, not bounded. But we can see that the intersection is also empty. Right? So it's empty. So we get that those two conditions, bounded, closed, they are very, very important. Actually, bounded closed implies compact. Right? Bounded closed set in R means compact set. So sequence, nested sequence of a compact set, non-empty compact set, has this property. This nested interval property is a property of a compact set. All right. Okay. Now let's state the Bolzano-Weierstrass theorem and prove it. Okay. The Bolzano-Weierstrass theorem. It's one of the important theorems in the analysis. So every bounded sequence of real numbers has a convergent subsequence. Has a convergent subsequence. Okay. Has one, it will have infinitely many because any subsequence of this convergent subsequence convergent. Okay. At the beginning of the proof, the author mentioned one general observation. So they are going to use this general observation many times. So what is a general observation? If we have xn, a sequence, and we have a set E, this E can be written as a union of two sets. And E contains xn for infinitely many values of n. So you see here, maybe xn is a constant number. Xn, for example, xn is always 1. So E contains 1, but xn corresponds to infinitely many values of the positions, index n. So we will say E contains x1, E contains x2, E contains x3. Even though this maybe they repeat it, the constant, but we will see we count them for infinitely many values of n. So even though you have n 1 1 1 1 1 all the time, but we will see we have them infinitely many times. Okay, if E contains xn for infinitely many values of n, then at least one of sets A or B contains infinitely many values of n, right? So because you only break it into two parts, you already have infinite many. You break it in two parts, at least the one part has to contain infinitely many values. Okay, so that's a general observation. It's like you have 3 elements, two boxes, one box will contain at least 2, right? 3 elements in 2 boxes, so one box will contain at least 2 elements. Okay. Now let's see the proof. So let xn be a bounded sequence. Xn be a bounded sequence. We choose A and B. Choose A, B in R, such that all xn's belong to the interval AB. Because it is bounded. Bounded means we can use a closed interval to cover all of values. All right. So now we set I0 with this initial interval AB. And then we divide I equally into 2 subintervals. So we will have A a plus b over 2. This is midpoint, and a plus b over 2 and b. Okay. Okay. You see now I0 contains xn for infinitely many values of n, actually all values of n, and I0 is the union of two subsets. Then by the observation we just mentioned, at least one of a plus b over 2 and a plus b over 2b contains infinitely many contains xn for infinitely many values of n. Okay, so we call that set I1. So I1 could be either this one or the other one. And we know that I1 has a length half of the previous one. This one, I0, this is I0, this is I0, I0, yes. It's 1/2 b minus a. Right? And continue. We divide I1 equally into two subintervals. Let's call it I1 is equal to I1 prime union I1 double prime. And again, you are going to repeat this. I1 contains xn for infinitely many values of n, then at least one of I1 prime and I1 double prime contains xn for infinitely many values of n. We've just repeated this observation. Okay? So we call that set I2. We call that set I2. And I2, like I1, I2 is just one of I1 prime or I1 double prime. And the length of I2 is half of the length of I1 is actually b minus a over 4. 4 is 2 squared. All right. So you see here, we already do it twice. You will see the pattern. Repeat this process. We have a nested sequence of in with the length of in is equal to b minus a over 2 to n. Here is a 2 squared because it's I2. Here is a I1 Where's the length? Length is b minus a over 2. So if you have in, it will be minus a, the length will be b minus a over 2 to n. All right? And in is non-empty, closed, and bounded. Non-empty, closed, and bounded. So the intersection E of all in will contain just one element. Where not a. No, let's see what letter they use. What letter they use? X. They use X. Right? Because this one converges to 0. When n approaches infinity, b minus a over 2 to n will converge to 0. So it has exactly one element. Okay. Now let's try to prove there is a sequence inside a subsequence of xn converge to x. In is non-empty. Then we will have x and k belong to in. X and k belong to in. Because in contains xn for infinitely many values of n. So we can choose that nk is always strictly less than n sub k plus 1. Okay, so for example, if you have one element, you see, this is right? So the bigger one divided by half, divided by half. If this element, it belongs to the first one, belongs to the second one, belongs to the third interval. You see, the first interval, and second interval, a third interval. It belongs to all of them. So you will not choose this x, the index, as a constant n sub k. Since this interval will contain a lot of other xn for different values of n, so you just choose the next one, the bigger one. That's possible because you have infinitely many choices, right? Okay, so we always have an. Here I just want to guarantee that this indices will increase. We do construct a sequence, subsequence. We do not have just repeatedly choose x1, 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 x1 all the time. Okay? So x and k in n is a subsequence of xn with x and k belong to ik. X and k belong to ik. Where is it? Here. This is k, not n. This is k. I1 you choose xn1, I2 you choose xn2. So this is ik. Ik. This k and this k, they correspond. Okay, check here. X and k, they belong to the same ik. So the distance between those 2 points, of course, greater than or equal to 0, and it's less than or equal to the length of ik. Length of ik is less than or equal to b minus a to power k. Actually, here, ik, it's this length is b minus a to the power 2 to nk. Nk is greater than k, greater than or equal to k, so it's less than or equal to b minus a to the over 2 to power k. That's a reason you have this step. I don't want this n sub k. I just want k. It's enough. All right. So by this condition, you can see that it is only controlled by this k. When k is bigger, increase, it will converge to 0. So by square theorem, actually by definition, not square theorem. By the definition of a limit, when k approaches infinity, x nk has limit x. Here, how do I get by definition? So for any epsilon greater than 0, there exists a capital K belong to the natural numbers. For all k greater than or equal to capital K, you require b minus a over 2 to k is less than epsilon, right? This is possible. And then you have this inequality. You have this inequality less than epsilon. You just require this one. And then by the definition. Okay, so you can understand this process. Okay, so this is the proof of the Bolzano-Weierstrass theorem. It looks very simple, but actually we have a lot of preparation to come up with this result. This is a very important result. It's used frequently. Keep in mind, every bounded sequence has a convergent subsequence. Bolzano-Weierstrass theorem. Okay, so we finished the section 2.3. In this part, there are many interesting exercises. In the exercise part on page 48, you can try problem 1, problem 2, let's see, the problem 4, problem 5, and problem 6. All of them are interesting. Let's just pick up those exercises. See if you can figure it out. Okay. All right. Okay, we finished the section 2.3. Now let's talk about the next section, 2.4, the Cauchy sequence. So Cauchy sequence solve the following question. So whenever we say a sequence convergent or not, we have to find the limit. We say, okay, the sequence is close to the limit, then the sequence itself converges. The limit is outside of the sequence. It may be outside. You may not see that number directly from the sequence. So the Cauchy sequence try to set up a property, the property of the sequence itself. You don't need to see the limit. You just study the sequence itself. If the sequence itself contains this property, then the sequence will be convergent. Okay, so it's an intrinsic condition, not the condition depending on the external information. Okay, so that's the definition 2.27. A sequence of a point xn in R is said to be Cauchy if and only if for every epsilon greater than 0 there is and capital N belong to the natural numbers such that n mn for all n mn greater than capital N, it implies ops value of xn minus xm is less than epsilon. Okay, so he check here, this is very close to the limit definition, but in the limit definition you need the limit, it's x minus x. That x does not belong to the sequence, but here this x and xm both are the elements of the sequence, so this is a sequence condition in itself. Okay, so let's see how we get the relation between the Cauchy sequence and the convergent sequence. 2.28 remark. If xn is convergent, then the sequence xn is Cauchy. It's a Cauchy sequence. Proof. Okay, so suppose xn converges to x as n approaches infinity. Whenever we say it converges to, it is convergent to, the sequence is convergent, we definitely know the limit, right? Okay, then let's write this by the definition. So for any epsilon greater than 0, there is an capital N in the natural numbers such that for all n greater than or equal to capital N, the ops value of xn minus x is less than, this time I'm going to put epsilon over 2. I'm going to put epsilon over 2. Okay, so also for any m greater than or equal to capital N, the same. N already satisfied the condition. For any m greater than or equal to capital N, xm minus x is also less than epsilon over 2. Right? Whenever your index is bigger than the this pre-selected index n, then you always have this property. Okay, so now the xn minus xm, we're going to have our traditional trick. We will xn minus x minus xm minus x. Right? And then we use the triangle inequality. And this one is less epsilon, this one is also less epsilon. It is less epsilon. So what we have, for every epsilon there is a capital number, capital N, such that for all n m greater than or equal to capital N, xn minus xm is less than epsilon, ops value less than epsilon. So this convergent sequence. This convergent sequence must be a Cauchy sequence. Okay. Okay, now let's prove the main theorem of this short section. Theorem, Cauchy theorem. Cauchy theorem. Let Xn be a sequence of real numbers. Then the sequence is a Cauchy sequence if and only if the sequence converges to some point. To some point in R. So basically this theorem just say it is a Cauchy sequence is equivalent to a convergent sequence. But convergent sequence you have to know it is the limit. You have to know the limit. Even though you don't know what the precise value, you know the limit exists. There is some place there. But Cauchy sequence does not care the limit. It cares the structure of itself. Okay? Okay, so technically, well, in the remark, it proves one direction. If it is a convergent sequence, it's a Cauchy sequence. Now we're going to go back to the other way. If it is a Cauchy sequence, we're going to find the limit and prove the Cauchy sequence converge to the limit. Right? So we're going to find and show it convergence. Okay, so we only need to show one direction. We only need to show that Cauchy sequences converge. Right? Cauchy sequences converge. That's the missing part. Okay. Okay. Now let's let Xn be a Cauchy sequence. Then Xn is bounded. Why Xn is bounded? You see, let me show why it is bounded. Let epsilon be number 1. There exists a k in N such that for Nm greater than or equal to k, Xn minus Xm is less than or equal to 1. Okay, so we just choose epsilon to be 1. Less than, no equal, less than 1. Okay, now we check. We have x1, x2, xk, capital K. What is xk plus 1? Xk plus 1. It is greater than xk. So xk plus 1 minus xk is less than 1. So this implies ups value of xk. Let's put ups value. Ups value of xk plus 1 is equal to ups value of xk plus 1 minus xk plus xk. Then by the triangle inequality, it is less than 1 plus ups value of xk. So this is a k plus 1, and k plus 2 you have the same property. So after xk term, by this Cauchy condition, it is all the elements will be less than 1 plus xk plus 1. Or 1 plus xk, no plus 1. 1 plus ups value of xk. So you choose a maximum of them, or you add them. So we just add them. We call it m. let m be the sum of all of them. Let me rewrite it. Right, okay? Then all xn will be less than or equal to m. So xn is bounded. All the Cauchy sequences must be bounded sequences. Okay, so you should be able to prove this in the exam. Okay, X is a Cauchy sequence, X is a bounded sequence, and Bolzano-Weierstrass theorem says every bounded sequence has a convergent subsequence by Bolzano-Weierstrass theorem. Xn has a convergent what? Convergent subsequence. Convergent subsequence. What is it? It's a, let's call it xnk. Okay, so there is a number x in R such that, okay, let's see. For all epsilon greater than 0, there exists a capital K in the natural numbers such that for all little k greater than or equal to capital K, xnk minus x is less than epsilon. Let's see, let's put epsilon over 2, whatever. You can just put epsilon there, it doesn't matter. Okay, so it's very small. Distance is very small. And let's continue. We find a limit, but this limit is the limit of this convergent subsequence. We're going to show that not just this subsequence converge to x, all the sequence will converge to x. All right, all the sequence will converge to x. Let's say, so choose for okay, xn is a Cauchy sequence. Then for the same epsilon, for this same epsilon, there exists capital N1 such that for all nm greater than or equal to capital N1, upper value of xn minus upper value of xn minus xm is less than epsilon over 2. Okay. Here is a k, capital K. Here is a N1. So we also choose this capital K to be greater than or equal to N1. We choose this capital K to be greater than or equal to N1. If this happens, then both conditions satisfy. Then let's see. The reason is that little k is greater than or equal to capital K. This implies n sub k is greater than or equal to capital K. Because n sub k is greater than or equal to small k and greater than or equal to capital K for sure. All right, and also it is greater than or equal to capital N1. Okay, now let's see. For all n greater than or equal to capital K. This time we're going to choose this capital K because capital K is greater than it. If here you don't want the capital K, you can let capital N2. Okay, here you can let capital N2 be the capital K plus N1. The same thing. You just choose a very large index, bigger than both indices, so that these two conditions you can apply together. Okay, so for all n greater than or equal to capital K, then let's check the ups value of xn and ups value of xn minus x. Okay, so we insert a random xnk. Any xnk will work. We random insert xnk, but we need this k to be big enough. Insert a subtraction and addition, and then you try triangle inequality. All right, and see, nk is greater than k is greater than capital K. So this, you apply the Cauchy condition. The first one, apply the Cauchy condition is less than epsilon over 2. N is greater than k. Nk is also greater than k. K is greater than capital N1. So the Cauchy condition is satisfied. It's less than epsilon over 2. And xnk minus x, we also require this k with this condition. So the distance between xnk and x is less than epsilon over 2. So it's epsilon. See? So for any epsilon, you have an integer capital K. For all n greater than capital K, the distance between xn and x is less than epsilon. So xn converges to x as n converges to infinity, approaches infinity. Right? Okay, so this finished the proof of the Cauchy theorem. The Cauchy theorem just tells us, even though we may not know the limit, the concrete value of the limit, but from the sequence itself, we can determine if the sequence converges or not. You just check the Cauchy condition. When the Cauchy condition is examined, then you will know it will be definitely convergent or divergent. We don't care, or we don't need to know the limit at the beginning. Okay? So sometimes the sequence does not have a concrete formula. If you do not have concrete formula, how do you know the limit at the beginning? You couldn't know it. You only know some property of the sequence. In that case, you can still use the Cauchy condition to predict the convergence or divergence property. Okay? Let's see here the example. In this example, we don't have the concrete the formula for the sequence. We only have the property. Prove that any real sequence xn that satisfies ups value of xn minus xn plus 1 is less than 1 over 2 to n for all n natural number n. This, whatever sequence like this is convergent. You see, you even have no formula, just have a condition. If there's no formula, you don't find the limit at the beginning. Okay, so here we need a condition, a non-result. One over 2 to n from 1 to infinity. This is equal to 1. This sequence is this series is equal to 1. Okay. This one is required. It's like this one. It's a geometric proof. You cut it in half. This is 1/2, the first term. You cut the rest in half. This is 1/4, second term. 1/8, 1/16. So you add all of them together. You recover the big square. That's 1. The area is 1. So 1/2. The area is 1/2. The left rectangle. This top right corner is has an area 1/4. This middle vertical rectangle has an area 1/8, 1/16, 1/32, and so on. So this series has a sum equal to 1. Keep in mind, this is important and convenient. How do we prove it is convergent? We're going to show it is a Cauchy sequence. So for two indices n, m, we just assume m is greater than n. We have xn minus xm. Okay, we want to measure the distance. It is, we're going to have the following thing: xn minus xn plus 1 plus xn plus 1 minus xn plus 2 plus xn plus 2 minus xn plus 3, and so on until xm minus 1 minus xm. So you just insert plus minus plus minus plus minus from n to m. Just connect them. You do not leave any breaks. Okay, and then you apply the triangle inequality. So you have xn minus xn plus 1, xn plus 1 minus xn plus 2, xm minus 1 minus xm. Okay, cut it. It's like you want to measure the distance from xn to xn minus 1, from xn to xm, you just cut and count the difference here, 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 here. Right? And then you can apply the condition. Each adjacent difference has ops value less than 1/2 to n. So it's less than 1/2 to n. It depends on the first index, n. So next one, 1/2 to n plus 1 until 1/2 to m minus 1. M minus 1. All right? And if we factor out the common factor, 1/2 to n minus 1, 1/2 to n minus 1, we will have 1/2 1/2 squared and 1/2 to m minus n. You see, this is a partial sum of this convergent series. The total is a positive convergent series. The total series is 1. The partial sum is less than 1. Of course, this sum is less than 1. Okay, less than 1 times 1/2 to n minus 1 is this. Right? Okay, so now we assume for every epsilon greater than 0, there exists a capital N belong to the natural numbers with 1/2 to capital N minus 1 is less than epsilon. So we need this condition. This condition can be verified. All right? You can use the natural log to find it. Then for all n greater than or equal to capital N, m, together with m. Of course, n and m, they have one relation. N and m, they have a relation. M is greater than n or n is greater than m. Let's just assume here, then you will have xn minus xm is less than 1/2 to n minus 1. If m is bigger than n. If m is less than n, it's m minus 1. But anyway, they are both less than 1/2 to capital N minus 1, and it's less than epsilon. So what we get is that this xn is a Cauchy sequence. You have a Cauchy sequence, it converges to a point in R. It converges to a point in R. All right? Okay, so that's very, very important. You see here, in this proof, in this example, we have no idea about the formula, but still, from this property, we can predict the convergence. We can predict convergence. And the next remark, you see here, we only estimate the distance between two adjacent numbers, xn minus xn plus 1. If it is smaller, the distance smaller 1 over 2 to n. But the remark says, if you only have this sequence converges to 0, it is not sufficient. It is not sufficient for Cauchy sequence. Here, we don't just need this one to be 0. We need you add something together. It is still too small enough. You see here, you add a lot of term. Actually, it can be infinitely many terms. It is still controllable. It's not just one term controllable. Okay? So the author provides an example. The example is this. The xn is natural log of n. Xn is natural log of n. First of all, it is unbounded. Of course, unbounded, not divergent. Unbounded divergent. But the xn plus 1 minus xn is natural log of n plus 1 minus natural log of n is a natural log of n plus 1 over n. This internal stuff will approach 1. Natural log of 1 is 0. So you have the difference of two adjacent terms converge to 0, but the original sequence diverges. Okay? So if you only have the distance less than approach 0, it's not enough. You also need to make that you add some together, add all the terms together. So, the sum will still converge to 0. I need this sum converge to 0. Also, this sum only depends on one number, not two numbers. Okay? Okay, so this is a remark 2.31. In this part, you can try the exercise on page 51, 1, 2, 3. Yeah, that's 6. 6 is interesting. On page 51, problem 1, 2, 3, and 6. Okay. All right, very good. Okay, we'll try this. They are very interesting, especially problem 6. Okay, we finished this video, and we will continue in the next one. Thank you.